Hey guys, this is Ayush back with another tutorial video. For this one, I'm going to be using a bit of contradiction and also proof by contradiction, and also a bit of contradiction to contrapositives, because especially later in the course, with more proofs as they come, you'll find yourself using contradiction to contrapositive a bit, because it's a really useful tool or technique. So yeah, let's get started. First one is kind of basic. Use proof by contradiction to show that a rational number cubed minus 996 is rational. And so what I would do is, let my camera, there we go. So I would put this into, sorry, the camera. Okay, so A is a rational, let's say A is a rational number. Then our statement is if P then Q. So if A is rational, then AQ minus 96 is rational. AQ minus 996 is rational. That's basically a summary of our statement, if P then Q. Now, if A is rational, it has to be equal to something over something. That's kind of the definition of a rational number. So let's say m over n. And then again, the definition of a rational number is this must be also equal to something over something. So let's do I over j. And then, okay, so it has to be proved by contradiction. So we have to show if P and not, so we have to show that P and not Q would lead to so we have to show that if we were trying to assert this, then it would lead us to be asserting P and not P, or we would be asserting Q and not Q, contradiction. So how we would do that is we would, let's see. Okay, so P is, so not P would be if A cubed minus 996 is irrational, and we would do that, so m over n so our P is that A equals m over n, and our Q, not Q is that, so this is our P, and then our not Q is that this. So how we would assert P and not Q is, okay, so we would say that, so not Q is at this, right? This statement is not Q. So now we would start solving it out. So m, this is solving out this statement, m cubed over n cubed minus 996. And then we would solve it out further, which is equal to m cubed over n cubed. That's just simplifying the fraction. And then we would, basically this is asserting that this is irrational. But if you really think about it, this statement is actually a rational number, because m is like a whole number, n is a whole number, n is a whole number. So it would actually lead us to a rational number by definition, especially when you consider the lemma that if m is rational, then m cubed is rational. That's the lemma. So that would mean that this is rational, this is rational, this is rational, and then we're just basically the whole fraction is rational. When not Q, basically by saying not Q, we were saying that it's irrational, but in reality it's rational. So that's where we're going wrong, and that's how we're asserting Q and not Q. So basically, because we were able to assert P and not Q would lead to Q and not Q, we just proved by contradiction that the statement above is true. Again, I'll summarize it in case I didn't explain it well enough. So if P then Q, that's the whole statement. If A is rational, then AQ minus 996 is rational. This is the definition of a rational number. And then if P, now by proof by contradiction, P and not Q would lead to Q and not Q. So our statement P is that A equals M over N, and then our statement not Q is that M over N cubed minus 996 is irrational. And then so we would solve it out, and we would arrive at this fraction, and then this fraction turns out to be, in reality, this fraction is actually rational, but then when we try to assert not Q, we were trying to assert that it's irrational, so we just led to a conclusion that Q and not Q. And our lemma that we're taking into mind is that if M is rational, or if M is a whole number, then M cubed is also a whole number. And that's how we knew that by definition, this whole thing would be rational. So yeah, that's the first problem. Now I'll move on to the second one. Okay, so, oh, this is not as basic. Okay, so use contradiction. Let it come into focus. Okay, use contradiction to contrapositive to prove that for all integers n, if n cubed plus 5 is odd, then n is even. And I just want to cite my source right there, so I'm not plagiarizing. So we have our statement P and we have our statement Q. We would do so contradiction to contrapositive. So basically, what we're trying to prove if P then Q. Now by contrapositive, we have to be proving if not Q then not P, and then by contradiction to contrapositive, we have to be proving if something and the not of something, which means if this and not P, then either Q and not Q or P and not P. So yeah. And then, yeah, we would simplify that to would lead to one of these. So not Q and P would lead to a contradiction. Okay, so we'd be doing, by the way, in case you were wondering why I would use proof by contradiction to contrapositive instead of just contradiction, it's because if I was to just use contradiction, I would have to prove it in a certain way. Like I would have to prove, I would have to first show that n cubed plus 5 is odd, and then derive n is even. But basically, I want to show it based on if n. Like I want to start with the if the smaller statement then the bigger statement, just because that like working upward is easier for me. So you kind of have to choose which method works better for you. For me, it's working upward. And yeah, okay, so I'm just gonna restate like what I did just there in case you don't understand. So our statement is if P then Q, contrapositive if not Q then not P, and then contradiction to contrapositive if this and not this, which means if this and not this would lead to a contradiction, and then I just restated that. So then next I would do okay, not Q, which means n equals odd, so n is 2j plus 1, and then P, so then n cubed plus 5 equals 2j plus 1. So this is our not Q, and then this is our P, and then so yeah, we're saying it's odd, and then we're saying it's odd. Now we would start solving it out, and hopefully we'd arrive at a contradiction in the end. So n cubed, so because n is equal to 2j plus 1, n cubed would be 2j plus 1 cubed plus 5, and then the plus 5. So yeah, and then that would be equal to, oops, I should have used a different variable here. Let's use k. Um, so yeah, that's odd as well. So 2k plus 1, and then, so then, yeah, this is definition odd number, but then what our goal is to prove that this will truly end up being even though we're trying to state that it's odd. That's how we do the contradiction proof. So then we would start doing that by multiplying this out first. We would have that be 4, sorry, not 4, 8 j cubed plus 3 times 2j squared plus 3 times 2j plus 1, and then the plus 5 is equal to 2k plus 1. And then this one, so all I do is just multiply this thing out. Next thing we do is we just simplify this. So oh wait, no, that's not 6. And we would change that to 6. Then as you can see, we would have, if we were to simplify it further, we would get to 4j cubed plus 6j plus. So there, if we were to simplify it further, we would get to, and then let's just say that this is I guess like L. So we would have 2L equals 2k plus 1, and even number equals an odd number, and that's wrong. Basically, we just proved that P and not P, that not P was trying to state that it's odd when we derived it, and we really got that it's even, so we arrived at P and not P. So we just prove by contradiction to contrapositive that this will lead to P and not P. I hope that fully made sense. I'm just thinking if I can explain, if there's any more I can explain about it. So if I were to write it out fully, I would have, so we would just prove that if not Q and P, there's a contrapositive statement. If that, then P and not P. So yeah, we just proved this. Contradiction to contrapositive.